Hey everybody, welcome to the channel. Today we're going to be looking at a number theory problem. So the problem says, are any numbers in this sequence ever perfect squares? And of course by perfect square, I mean an integer squared. Right, so we have 11, 111, and then the next terms in the sequence are just made by adding a 1 at the end. Right, so this is a bit of a weird problem, and I guess the hardest thing about this problem is where do you start? Right, so pause the video and have a go for yourself. Alright, well I'm going to jump straight into it. I'm going to rewrite all these terms in the sequence in a slightly different form. So I'm going to keep the 11 the same, but then I'm going to rewrite 111 as 100 plus 11. And I'm going to do the same thing for all the other terms. Okay, so I'm going to rewrite this as 1, 1, 0, 0 plus 11. And I'll rewrite this as 1, 1, 1, 0, 0 plus 11. And in general, you know, the general term, which is represented by this with the dot dot dots, can be written as, well, you're going to have 1, 1, 1, and, you know, some amount of ones. Should we keep this the same? Right? And then we're going to have 2 zeros at the end. And then we're still going to have to add on the 11 to make it the same as it was previously. Okay? Okay, and why is that useful? Well, now we can introduce ideas of divisibility. Right, well, if we look at all these numbers, if we look at 100, 1,100, I guess that's 10,000, 11,100, right? And we look at all these numbers, well, what do they have in common? Well, in fact, they're all divisible by 4, right? Well, of course, I mean, 4 times 25 is 100, and then, of course, 4 times 250 is going to be 1,000, 4 times 2,500 is going to be 10,000, etc. And this number, well, this is 100. This can be split up as 1,000 plus 100. This can be split up as 10,000 plus 1,000 plus 100. Just this part in blue, right? So we see that all the terms in blue are divisible by 4, right? And then we still have the plus 11 at the end, right? So let me just get some tissue, work this out. Okay, so how does that help? Right, well, we can rewrite this part as, okay, so we have 11, and then we have 4k plus 11, right, for some k, right? Maybe I should label it k1, and then we have 4k2, some integer k, we don't know what it is, you know, plus 11, etc., etc. Okay, but we can do even better than that, right? Because 4 goes into 11, okay, but there's a remainder, right? So we can rewrite this again, right? So instead of plus 11, we can write this as, well, what's the highest multiple that goes into 11 from the 4 times table is 8, right? So we have 8 plus 3, and then we have 100 plus, what's going to be 8 plus 3, and then etc, 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 right? So I can break these 11 into plus 8 and plus 3. And how does that help? Well, again, 8 is part of the 4 times table, right? And so are all these parts in blue, okay? So what can we conclude from that? All the terms in this sequence can be expressed as this, 4k plus, well, we had the plus 8, which was divisible by 4, but then we had plus 3 left over, right? So all of this form. Okay? And just to be very explicit, I'll just rewrite this. Okay, so take this, the 111 dot 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 dot, with 11 at the end. Well, I can rewrite this as 1111 dot 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 08 plus 3, and we already said that this part is divisible by 4. Okay? And how does that help? Well, now we can just analyse what we know about perfect squares, right? So again, perfect squares are the squares of integers. Well, all integers are of the form 4k, 4k plus 1, 4k plus 2, or 4k plus 3, right? If we go up to 4k plus 4, okay, then we can, there's a common factor of 4, so it'll be 4 times k plus 1, okay, which is 4 times another integer, right? So all integers are of one of these forms, okay? And now let's just consider what happens when we square them. Okay, so if our integer is of the form 4k, and then we square it, we're going to get 16k squared, which again I can rewrite as 4 times 4k squared. Okay, so it's of this form. Okay, so this form of number squared produces another number of this form, right? Let's go ahead and see what happens when we square 4k plus 1, right? Well, you might see what happens here. Okay, we're going to get 16k squared plus 8k plus 1. Okay, and again you could factor out 4 from here, but then we're going to have a remainder of 1. Okay, so this squared produces another number of the form 4k plus 1. Okay, this case is slightly different, but let's try it, let's see what happens. Okay, so we get 4k plus 2, and then we square that, well, we're going to get 16k squared, plus this times this is 8, so we have 8k, but then we have to times 2 again, so we're going to get plus 16k, and then 2 squared, well, that's going to be 4, right? And we see 4 is a common factor, so we're going to take that out. So we get 4 times 4k squared plus 4k plus 1, right? So a number of this form squared produces a number of this form, right? Because this thing in the brackets here is going to be an integer. Okay, so let me just do the final case. Okay, so 4k plus 3, when we square that, right? What's going to happen? Okay, well I could write all this down, or I could just look at the final digit, right? This plus 3, because that's what's going to matter. Okay, 3 squared is 9, okay, which is 8 plus 1, right? 8 is divisible by 4, so when this is squared, we're going to have something plus 8 plus 1. Okay, so the remainder when divided by 4 is going to be 1. Right, I hope that's not too confusing just to say out loud, just so I don't have to write it down. Okay, so what forms do we have? Right, when this was squared, it was of the form 4k. When this was squared, it was of the form 4k plus 1. When this was squared, it was of the form 4k, we already had. And when this was squared, we had something of the form 4k plus 1. Right, so that's it, we're done. All squares are of the form 4k or 4k plus 1, but all the numbers in this sequence are of the form 4k plus 3. Therefore, none of the numbers in this sequence are ever perfect squares. Right, because this doesn't match with this. Hope you enjoyed. See you next time.
Hi guys, don't forget to subscribe to Mad Maths.